coming Saturday is a student event. The following Saturday is holiday. So quiz 4 is scheduled on 11th November. The usual 8:30 to 9 slot, distributed among the 3 rooms, L18, 19, 20. Syllabus, everything after the mid-semester exam. You will not require any handout. Just come with your pen, calculator, and adequate preparation. So we are talking about Navier-Stokes and the difficulty in solving Navier-Stokes equations. We look at limiting cases and see if some solutions can be built up. One limiting case, well, actually we have already seen fully developed flow where the inertia terms are identically 0. Then we looked at the limiting case where Reynolds number is small, for which the inertia terms are dominant compared to the viscous. What did I say? Where the viscous terms are dominant relative to the inertia. So just a remark that in fully developed flow, the inertia terms are identically 0. Giving rise to the Stokes equations. These are the Stokes equations. So applying these equations to flow past a sphere. So naturally the gradient operators and the velocity components have to be expressed in spherical coordinates. So the flow is aligned with the z direction. XY is a cross plane, R is a polar coordinate in spherical coordinates. So if you want to relate it to x, y and z, R square is equal to x square plus y square plus z square. Phi is an angle measured relative to the z axis. Radius of the sphere is r. I think I commented on this point earlier and I want to repeat that we use a radius because our radial coordinate may go from 0 to r or from r to infinity as in this case. But all measurements are carried out with respect to diameter, so you have to express your final answer in terms of diameters. You may say, what is there between radius, diameter? It's all the same, but it helps build communication. U is the approach velocity. So, if you consider a slice of this sphere, so that will be a circle. So, it will look so this will be the xz plane sorry, xy plane. I am talking about the cross plane. This is the cross plane, and the radius will be r sin alpha, r sin phi, and this angle measured from the x axis is theta. So, that makes it the r theta phi coordinate system. But all around the sphere in the theta direction, we expect the flow to be unchanging. That means, there is no dependence of any of the flow variables on theta. So, it's a kind of symmetry, it's all around. This is the thing you can imagine. This is the sphere, flow is in this direction on a plane at right angles to the flow. There is no variation in that direction. It's very similar to no dependence on theta for flow through a tube. The circumference of this ring element will be 2 pi r sin phi, and the thickness will be r d phi. So, this entire development is in red. So, I am not going to solve these equations, but I told you, I gave you a hint. The first step in solving such equations is to decouple velocity and pressure. So, you do a del dot of the momentum equation, you get del square p equal to 0, solve for pressure, put that in the momentum equation, and you have a Poisson equation for velocity that can be solved. So, these solutions can be obtained using classical tools as outlined by Kreyszig or equivalent. Algebraically, it becomes a little more complicated because of spherical coordinates, where the curvature terms are, let us say, formidable. So, the velocity components are u r, u phi, and these are functions of r and phi. Similarly, p is a function of r and phi, and the solution was written last time. So, just repeat those solutions. So, this is a new approach. Some simple problems you can solve on your own. Somewhat more complicated problems, the solution will be given, and you will be expected to certify that it is a correct solution. How do you certify? You substitute the solution in the governing equations and check if you have left hand side equal to right hand side, and then also check if initial conditions are satisfied if it is an unsteady problem, and boundary conditions in all others. The boundary conditions here would be at r equal to capital R, the no slip condition will hold. That means u phi at r equal to capital R is 0, and then the normal velocity u r is also 0 on the surface. these two conditions. Far away, these components will become equal to the approach flow. The far field is undisturbed. Okay. So, around this sphere you have a zone of disturbance. You also have to realize that a problem of this type represents not just flow past a sphere, but also a sphere moving in a stagnant medium. So, at least geometrically speaking, you could think of it as a raindrop falling in air. It's also represented by the same configuration, but then you have to ask, is Re less than 1? Usually no. Okay, but dust particles in water will have Re less than 1. So, sometimes students ask, what do I do if my Reynolds number is not less than 1 because this solution does not hold? Well, the answer is categorical. Please go back to Navier-Stokes equations and solve the system, if not analytically, by an approximate tool such as a computational technique. So, you might have studied such solutions in a different context. You can see that the right hand side, P infinity is the undisturbed pressure. So, the right hand side is the disturbance which decays as small r square, square of the radial coordinate. So, rapidly diminishes with distance from the center of the sphere. The radial velocity component and the angular velocity component So, pressure will give rise to, pressure distribution will give rise to a force acting on the sphere. So, if you look at drag, I think we have used the same symbol for diameter and drag. So, just to avoid confusion, let me use the symbol x. That is the, I think here it will be because it is in the z direction, we will just leave it as drag. We will have components arising from normal stresses and shear stresses. It has a normal component arising from pressure distribution and shear stresses. So, if you look at a portion of this sphere, normal and shear. This is a part of the sphere, and these have to be evaluated on the surface of the object. On the surface, we have the no slip condition, and I showed you some intermediate steps that on the wall, on r equal to capital R, this becomes minus p, and sigma r phi on r equal to capital R becomes mu partial derivative of the tangential component of velocity with respect to the radial coordinate. So, these stresses have to be evaluated on the surface of the sphere, So, for that, since there is no dependence on theta, we can choose this ring element of radius capital R sin phi, perimeter. So, the elemental area will be 2 pi r sin phi times r d phi. On that, you have these stress components acting, and then you can decompose them into the x and y components. Now, because of the symmetry of the flow, the total force acting on this sphere in the vertical direction turns out to be 0, that you can show. So, the viscous part is equal to integral. Now, I am sorry, this phi goes from 0 to pi. That way, those rings will cover the entire surface of the sphere. So, this is 0 to pi sigma r phi at r equal to capital R, 2 pi r sin phi r d phi, and then we have to work with the component of sigma r phi in the x direction. So, sigma r phi in the flow direction would be sin phi. And sigma r phi is to be found from the velocity distribution. So, and you said r equal to capital R. So, that will turn out to be 4 pi mu r u r, and the contribution due to a pressure distribution. Now, often it is called form drag. The reason for using form is geometry, shape, and shape changes, the pressure distribution changes drastically with the shape of the object. That is a topic we will study as we go along. So, the force acting on the object arising from a pressure distribution is often called form drag or form lift, as the case may be. Okay, so, right now we are talking about drag. So, it is form drag. So, there was sigma r r, which is minus p at r equal to capital R. Then the area element and then the component, which turns out to be 2 pi mu u r, and so drag is equal to 6 sum of the 2, which is called Stokes' law. The reason it is elevated to the status of a law is because it is one of the earliest solutions of the Stokes equations. Of course, the solution becomes important only if it matches experiments. Have we seen experimental data? Yes. For that, we have to express the result in dimensionless form. So, CD is drag divided by half rho u square times the projected area. How much is the projected area for a sphere? Not the surface area, flow and pi r square, right? Drag, and then we want to relate it. You have done dimensionless or dimensional analysis of such problems. You know, drag will turn out to be a function of Reynolds number. And then if you just convert this d equal to 6 pi mu u r, turns out to be 24 over RE. Okay. So, if you plot on a log scale, this should be a line. Okay, and this we know will be valid up to 1, and then there is some departure, and then it becomes nearly constant, and then there is a dip, and then again there is an increase. This is the overall variation, but this is the Stokes regime. We have been able to reproduce this part of the curve. So, what is the flow pattern? Well, you have the velocity components, so you can get the velocity vector all around the sphere. So, flow will go around the sphere like that, all around. So, So, the second one, the one below, this is flow past a sphere. This initial part, you can see it says 1, this I have given you, you may want to check it. It says Stokes theory. So, the first part is CD versus RE, that initial part is 24 over RE. So, that part is reproduced against experiments. So, you can see all those circles, open circles, shaded circles, partly shaded circles, they represent experimental data. So, you can ask, how do I do an experiment? How do I find the force on a sphere? How do you find, we said small particle, how do you find the force acting on it? Suppose you wanted to check it yourself, what would you do? How do you measure force acting on a moving object? Acceleration. Acceleration is inertia is 0 in this formulation. But you can wait for acceleration to become 0, because you have time on your hands, I think. So, you remember the particle tracking experiment we talked about long ago. You drop a small particle through a column of oil, let it accelerate and attain terminal velocity. Under terminal velocity, this is called gravitational weighing, because that weight and drag will balance each other and acceleration becomes 0. So, then you can say that the drag is balanced by weight. So, and you know the weight, effective weight, that means mg minus buoyancy. So, that is a way of, that is a method of weighing. Suppose you want to find force, you have a spring, you let it act on the spring and let the spring deform. The deformation will give you the magnitude of that force. Similarly, here under moving conditions, that was a static situation. Under moving conditions, you balance hydrodynamic force with gravitational force. So, that is how most of these experiments have been done. Let us also look at the video if it will work. This is flow past a cylinder, which is very similar to here. So, these green lines will tell you the flow path. See, they go around. It's called the term used is they conform to the shape of the object. It's a video. It's called attached flow for reasons we will again discuss maybe on Wednesday. Okay, so that's the solution we have obtained. In the Stokes regime. So, just going back to pressure variation. So, the video shows that flow please mark this word, flow is attached to the surface of the cylinder. Now, if you look at pressure variation, that pressure was see minus 3 over 2 mu u r cos phi over r square, set r equal to capital R, and so you will have a variation at phi equal to pi, which is here on the left hand side. Cos phi is minus 1. So, it is a positive quantity, and phi equal to 0, cos phi is 1, so it is a negative quantity. So, it is a maximum upstream and it is a minimum on the rear side downstream of the cylinder. So, it is a maximum on the left and minimum on the right. So, if you plot let us say you plot p as a function of phi, at phi equal to 0 it was a minimum, and what is the variation? It is a cosine variation. At pi over 2 it is p equal to p infinity, cos phi is 0 and it is a maximum here. So, let me just show it like that. Okay. It is a cosine variation. So, here it is maximum at pi and it is 0, and here it is a minimum. And what is the flow direction? What is the flow direction? It is from phi equal to pi to 0. This is the flow direction. So, you see that pressure continuously decreases in the flow direction. Okay. So, if you think of pressure gradient, it is a negative with respect to the flow direction. It is very similar to flow through a tube where pressure decreases in the direction of flow. Like attached flow, there is a term that is used for this kind of pressure variation. It is called a favorable pressure variation or pressure gradient. Okay. So, pressure decreases in the direction of flow. So, why is it significant? It is also to be studied, because very soon we will look at the other limit of Re approaching infinity. Okay. So, we will be able to compare and contrast the two. So, for small Reynolds number, flow remains attached to the surface of the cylinder, CD scales inversely with Reynolds number, and pressure decreases on the surface of the cylinder, pressure decreases in the direction of flow. Okay. So, with this background, we move on to the other extreme and time to change the pen color from red to not blue, green, because it's important, it is relatively simple, hence exam friendly. So we now look at the other limit of inviscid flow. From the next class, we will go back to the blue pen. I am just trying to contrast red with green. So, what is inviscid flow? It is one in which in Stokes flow viscosity is so important. So, look at the other extremes. Why are we looking at extremes? Because if you work with full Navier-Stokes, you just can't make a start. It's too complicated. So, mu is 0, which means Re is infinity. I do not want to say Re equal to infinity. So, let me just say, but in real terms, it is much greater than 1. So, under these conditions, Navier-Stokes equations will reduce to the Euler equations. Okay, given by del dot u equal to 0, minus gradient of p. Now, if you have to write this equation in dimensionless form, all you have to do is drop density. The same equation will hold in dimensionless form. Okay, because Re is infinity, we have dropped the viscous terms that come afterwards. P, as before in both formulations, P will be modified pressure if gravity is important. So, that depends on the application being studied. So, we discussed this formulation in the previous class. So, Euler equations per se are complicated because of the non-linearity. This is a non-linear acceleration term, but it affords great simplification if you introduce an intermediate variable called vorticity omega, which is del cross u dot k. So, this dot k is required if you are going to carry out 2D calculations, otherwise you just do not have dot k, it is still vorticity. Then it is a vorticity vector, but right now we are talking about scalar vorticity. So, in the previous class, we interpreted vorticity as the rotation of a fluid element. The deformation rate scales with the shear stresses, while the rotation rate is called omega, the vorticity. So, this is a deformed fluid element, and this delta 2 minus delta 1 plus delta 2 divided by 2 was taken as the deformation of the fluid element, but delta 2 minus delta 1 is the rotation, and if you do a if you do a time derivative, it becomes the rotation rate, which is del cross u. So, in Cartesian form, omega is Vx minus uy. Yes. while Vx plus Uy divided by 2 would be the shear strain rate of shear strain of that element. It's a Cartesian form of the vorticity quantity. The advantage of introducing vorticity is it simplifies the momentum equation. So, if you do a del cross of the momentum equation, del cross del p is 0 and the acceleration term reduces to which in compact form is d omega dt, the total derivative equal to 0. So, this first you may remember. So, you will have to go back and check up that the first this expanded form is, I think these names keep appearing over and over again. We have Euler equations, Euler form, Newton's laws of motion and Newtonian fluid. This is an Eulerian form of, for acceleration it was acceleration, here it is the Eulerian form of the time derivative of the vorticity, and this is the Lagrangian form. And the two are equal, the two are, they form a mathematical identity, that d omega dt is equal to this expanded form, that is a mathematical identity. The Lagrangian form, just to jog your memory, is evaluated along a flow path which in our language is along a streamline. Now, d omega dt equal to 0 by itself is not very useful, because you have to integrate it along a flow path. That was the difficulty with the Lagrangian form anyway. So, but it becomes useful for a certain class of problems. So, not for any problem, but suppose you have a class of problems where you have an approach flow, a uniform approach flow. Going past an object. This is an object. An object is a site of disturbance. Flow goes around it. Because of the disturbance of the flow, the fluid accelerates and the object will experience forces. So, suppose you pick one streamline, say this streamline, then along this streamline d omega dt is 0, which means if I pick this point A here and point B here, I will have omega b equal to omega a as per the Lagrangian form of the vorticity equation. But how much is omega a? Because at A, u is equal to capital U and v is equal to 0. So, omega a is 0, b is any point in the flow field. So, omega b is equal to 0. So, if you have uniform approach flow, you get a very strong result that the vorticity of the fluid particle d omega dt equal to 0 tells you it is conserved in a way. Okay. But for uniform approach flow, omega is 0 everywhere. So, instead of solving these hard looking momentum equations, that is del u del t plus u dot del u equal to minus gradient of p, instead of solving that equation, you solve now a revised system del dot u equal to 0 and omega equal to 0, which in Cartesian coordinates will become u x plus v y equal to 0 and v x minus u y equal to 0. So, this sure enough it does not have pressure. What happened to pressure? We did del cross, so the pressure part of it went away, but you need pressure, right? Because if you talk about the force acting on the object, what are the shear stresses? Mu was 0 in this formulation. So, viscous forces are 0 on the object, forces will arise only because of pressure. So, you need pressure, pressure is very important. And there we work with the integrated form of the Euler equations. You remember this integration along S n coordinates, where S is along the velocity capital U. So, this will be u comma 0 at any point, capital U is the total velocity. By the way, I am using the symbol capital U for approach velocity, which is a constant, and I am also using it for the resultant velocity at any point. There is no reason why those two velocities have to be equal. The velocity itself is changing from point to point. So, this integrated form of Euler equations will give you, what will it give you? We discussed it last time. Bernoulli, some people call it Bernoulli equation, some people call it Bernoulli's equations. Which is constant. This is the steady version. There is a slight alteration that you have to carry out for the unsteady form, but we will not have time to look at unsteadiness. And here this capital U square is u square plus v square. Okay. And then integrating pressure will give you the forces. Okay, so now we have slightly altered the procedure for solving for the flow field. Find velocity components, find pressure from pressure from Bernoulli's equation, integrate pressure on the surface of the object and find forces. It's the new approach in the limit of RE approaching infinity. So, then the question is, how do you find the velocity components? Those are to be found by solving the mass balance equation and the vorticity equation. Now, vorticity, okay, so now let us move on to computation of the velocity field. I should not say computation, I should say calculation. So, since omega is equal to del cross u dot k and omega is 0. So, what is the form of u? U must be expressible, u is the velocity vector, as the gradient of a potential, here it is called a velocity potential. So, u must be expressible as gradient of phi. Then del cross u is identically 0 and omega is equal to 0. That will satisfy the vorticity equation. So, this phi is called the, you can see that we are running out of symbols. Phi was also the polar angle in spherical coordinates. Here phi is a velocity potential. Okay, so if you know phi, then you can find u. Okay, so but then how do you find phi? That can be found with reference to the mass balance equation. So, since del dot u is 0, del dot del phi is del square phi. So, phi has to be it's called it's a solution of Laplace equation. It's also called a harmonic potential. So, phi is a function that satisfies Laplace equation. So, the procedure is, so now we are talking about solving for velocity, pressure, forces. So, if you can find phi, you can find u, you can find pressure, and you can find in general forces and moments. So, this is now the procedure for solving for the flow field in the limit of Re approaching infinity. Now, once again, instead of solving, so this, how do you solve del square phi equal to 0? There are at least 68 million methods of solving this equation, and a few of them are outlined in Krasik's book. But to keep matters simple, what I will do is, I will give you representative solutions and ask you to show that they indeed represent a flow field. Let us look at one example. Phi, we are talking about 2D Cartesian. Suppose I give you this result, phi x y equal to u x. Certainly del square phi is 0. What is del square phi? Phi x x plus phi y y. And then u is equal to gradient of phi. So, the x component will be phi x, which is capital U. V is equal to phi y, which is 0. There is no y here. So, what does it represent? Just uniform flow. So, in terms of velocity potential, uniform flow is represented by u x, product of u, and capital U is the magnitude of the incoming velocity, and this is flow to the right, from left to right, if u is positive. Let us look at another example, and this time it is in polar coordinates. Okay, so just to refresh your memory, r is equal to square root x square plus y square, and theta is equal to tan inverse y over x. So, Cartesian and polar, they are completely equivalent. So, if this is the functional form, show that del square phi is 0. This is a valid, so if you say del square phi is 0, then it means that the expression given is a valid velocity potential. What is del square phi in polar coordinates? Okay. So, here is a problem for you, which we will take up again on Wednesday, but come prepared. Show that this is a valid potential, which means del square phi is 0. And then try to anticipate what flow field it represents. Okay? So, we will adopt this approach. I will give you the potential, I will ask you what is this flow field. Okay? But is it a bona fide flow field? For that you have to check if del square phi is 0 and if boundary conditions are satisfied. Okay, so just one last comment that we are now oscillating between chapter 4 of the book and a little bit from chapter 8 of the book. Okay. So, all right, so yeah, I'm just suppressing a needless comment.